Welcome to 27th lecture on numerical analysis. We started studying numerical integration in our last lecture, but in this lecture we'll continue the trapezoidal method of numerical integration that we started studying in our last lecture. So before we solve another example related to trapezoidal method, let's do a quick recap. We're going to find an integral to compute the integral for f of x, and this is the definite integral, and the limits are a and b. The lower limit is a, the upper is b. So the technique is that we divide this interval a and b into sub intervals where n is the number of interval. N is the number of intervals, right? x0, x1, x2 up to xn, and we can also write this integral from a to b as from x0 to x1, and then we can split this whole into small integrals, assuming that the shape of the function is linearly increasing or decreasing during each interval. So this is the approximation. This is a kind of approximation, and once we do that, this becomes a trapezoid, and in our last lecture we studied the formula to find the area of a trapezoid. That is the area under the curve, right? And if we apply this, as we assume f of x to be linear in this interval, so it becomes trapezoid, and the area of trapezoid can be written like this. So this is an approximation, and the same approximation can be assumed for the second sub interval, and we keep on going unless we reach to the final interval. We apply the same approximation, and then we assume these interval widths to be constant. This width is equal to this width is equal to the last width, right? So width of the intervals is assumed to be constant, and the width is h, which is 1 over n. So you can replace this as h, this as h. We can replace this with h. So h by 2 f of x0 plus f of x1. So if we solve it further, we reach to this equation we studied in our last lecture, and let's call this equation as equation number 1. Let's call it equation number 1, and now we are going to solve another example. We solved one example in our last lecture. Here we're going to solve the second example. F of x is 1 over x, and we are supposed to find the integral, the definite integral between 1 and 2 for this function 1 over x, right? We assume n is equal to 2 and h is 0.5. So actually we have assumed it to be, assume n is equal to 2. It's not given. We can assume n is equal to 4 or 8, whatever n we want. So h would be 1 over n, that is 0.5. So we use equation number 1, this equation. H is 0.5, 0.5 divided by 2, f of x naught, f of x evaluated at the first interval x naught, at the start of the first interval, f of x1 evaluated at the start of the second interval, and finally x of n, which is x of 2 in this case, the end of the last interval. So f of x naught, this is f of x1, and this is f of x2, and we studied that all these values x1, x2, x3 would be multiplied by 2 if they are not the initial, if they are not the initial and the final value, and we don't have this 2 multiplied with initial and the final values. So with all other values we have 2 multiplied, right? And this is the proof. We can convince ourselves for this 2, and this 2 isn't there for the first and the last value. And then we put it 1 over 1 plus 2 into 1 over 1.5 plus 1 over 2, because x naught is 1, x1 is 1.5, x2 is 2 here, x0, x1, x2 is 1.5. This is 1.5, 1.52. So the answer is 0.708. So using trapezoidal method with n is equal to 2, we get 0.708 as our answer. But let's see what's the exact answer. We just integrated 1 over x. The integral of 1 over x is log x, and we put the limits. Log of 2 minus log of 1 is 0.693. So this is the exact answer. Actually, this is the exact answer. Let's find the percentage error, which is the absolute value of actual minus the approximate answer divided by the actual multiplied by 100. It comes out to be 2.16%. So let's see whether we can reduce this error. Yes, we can. We can do that by repeating it for a higher n. Previously we did it for n is equal to 2, and we get an answer that is 2.16%. That the percentage error is 2.16%. So now we are going to try n is equal to 4, and let's see whether we can improve this percentage error. Improve means we can reduce this percentage error, because percentage error should be ideally 0, right? So let's begin solving the same problem using n is equal to 4, and now h would be 0.25. so once again we'll use equation number 1. This equation, h over 2 f of x0 plus 2 f of x1, 2 f of x2, 2 f of x3, 2 f of x n minus 1, but f of xn, not 2 f of xn, but fx of n. Right, so 1 over is f of x0 plus 2 times f of x1. F of x1 is 1.25, because now we are working with n is equal to 4. This means we'll have these 5 values: x0, x1, x2, x3, and x4. Right, so all these middle values are multiplied with 2, and these aren't multiplied with 2, actually they are multiplied with 1. So let's solve this, and it comes out to be 5.57, and if we multiply it with 0.125, which is 0.25 divided by 2, it comes out to be 0.97, a value that is very close to the exact value. The exact value is 0.693, so it's closer compared to this value 0.708 that we obtained using n is equal to 2. So choosing a higher n is equal to 4 actually have led us to a value that is closer to the exact answer, 0.693. So let's find the percentage error for this new value, 0.697, that we have obtained by putting n is equal to 4. So we do that, and it comes out to be 0.58%, whereas it was 2.16%, 4 times higher, approximately 4 times higher when we chose n is equal to 2. So this means choosing higher value of n actually reduces your percentage error and brings you closer to the exact answer. Right, so this is what we have learned here, and at the end of this lecture we have a homework, and you are encouraged to solve the same problem for n is equal to 8, and you will get a percentage error that is even smaller than 0.58%. Right, that would be a good exercise. Thank you. That's all for this lecture.